Hello and welcome to Disseminate the Computer Science Research Podcast. I'm your host, Jack Wardby. Today we are joined by Lukas Vogel, who will be talking about his cider paper, Data Pipes, Declarative Control over Data Movement. Lukas is a PhD student at the Technical University of Munich, and his research areas are adaptive storage and non-volatile memory. Welcome to the show, Lukas.
Yeah, thanks for having me.
Great stuff. Can you start off maybe by telling us a little bit more about yourself and how you became interested in researching databases and data management?
Yeah, okay. So like you said, I'm Lukas. I'm currently a fifth-year student at the database group at TU Munich, and I'm now more or less pretty close to submitting my dissertation. Towards getting to database research, I think I was always interested in programming close to the hardware, like think about cache locality, associativity, where that kind of stuff matters, right? Where you have to think about SIMD instructions and so on. And I never thought about databases of being in this context, right? But at TU Munich, the database chair is very close to hardware. So during my master's, I attended a lecture where we actually had to build our own database system in C++ from the ground up with Professor Neumann. And this kind of showed me that database could be very close to hardware. And then I started there and I never regretted it. So that's my path to database research.
Amazing. Trying to build a database from scratch as a master's sort of project is quite a daunting task, right? I bet that was fun.
Yeah, really fun. Like, of course, we didn't do everything, right? But like we got it to execute SQL queries, and a lot of fun, a lot of hard work. But I think that's a lecture I learned most at the whole master's and bachelor's degree, because I actually had to build some stuff.
Amazing. Yeah, sounds great. Cool. So let's talk about the star of the show today, data pipes. So declarative control over data movement. Can you maybe give us the high level sell for this, kind of the elevator pitch?
Yeah, of course. So I would say most programs that are performance critical or algorithms probably are a lot about data movement as well, right? You have data on some disk or somewhere. You then have to move it to your CPU through DRAM caches and so on, do some stuff with it, then maybe buffer it somewhere, get it back, and all that kind of stuff. So you have a lot of data movement already in algorithms, if you think about it or not. And of course, hardware manufacturers noted that, and they try to introduce shortcuts for users to use without using the CPU. So the CPU would be free for computation. So that is what brought us DMA, direct memory access, and stuff like this, right? The issue, however, is that those shortcuts are often bottom up, right? So you're not meant as a developer to know about those shortcuts. The hardware thinks about them and tries to activate them whenever it's a good thing to use them. So that movement happens implicitly. For example, think about using mmap, right? You mmap some memory region, and then your operating system thinks about when to move that stuff actually into your DRAM, and then the CPU thinks about when to moving that stuff into cache. But however, this is hard to use, right? This is all happening implicitly, and if you want to do it better than what the hardware figures out by itself, you have issues, right? And for those reasons, we present the vision of data pipes. So the idea is, instead of this bottom-up approach where everything is happening implicitly, we say, why not do data movement top-down, right? You as the developer explicitly state which data you expect to be where and when to move it to where you need it, so you can make more efficient use of the resources of your system. That's kind of the abstract elevator pitch, I would say.
Amazing. That's really cool. I guess we maybe, as we dig into this a little bit more, maybe you can start by telling us a little bit more about sort of the modern storage hierarchy, right? And there's a lot of acronyms in this space, right? So maybe you can sort of give us an overview of what all these things mean, and kind of the primitives we have available today.
Yeah.
You told me a little bit there. We need the high level cell, but talk about maybe some more of the other primitives we have.
Yeah, then actually there was a lot of issues, right? Like when we started talking about that stuff in the research group, lots of acronyms I didn't even know, and really hard, right? So I'll give you the overview of the most important ones, I'd say. So I think the issue nowadays is you just have this classical storage hierarchy, right? You have HDD on the bottom, really slow, then you have your DRAM, and then you have your caches and your registers and so on. And this has been true for 40 years, and applications have been built around that kind of hierarchy. The operating system expects this hierarchy to be there and so on. But the issue nowadays, we have lots of new devices that kind of fit in this hierarchy, but not really. So for example, we have NVMe SSDs, which are a lot faster compared to the old SATA SSDs, also more expensive, but mostly worth it, right? But they are attached over PCIe Express, for example. Then nowadays, like it's been killed now, but like a year ago, we had Intel obtains persistent memory, which is like DRAM, right? You do it, address it via load and source instructions from the CPU, but it's persistent, right? You can shut the system off and you still have your memory there. The downside of it is it's slower than DRAM, so it's not just a drop-in replacement. It's like slower by a factor of 2 or 3 or something. Then, of course, we also have network, right? So we can have everything that is attached locally. We can also attach it remotely via some network interconnect, via RDMA. We nowadays even have disaggregated storage over like CXL, which also works over PCIe Express. So yeah, so this pyramid is like lots of weird attachments to the side now. So it's really hard to manage. And of course, everything in this pyramid is also accessed differently. So some stuff is accessed quite easily, like for example, SSDs over NVMe. That's just a protocol you can use, or like your operating system can use. But then we have kind of those leaky abstractions. For example, if you think about the cache, in history never really meant to know about the cache, right? It's there to be transparent. So you just access some stuff and then it will be moved into the cache by the CPU and will be flushed when you don't need it anymore. But nowadays, for example, with persistent memory, we kind of need to have control over the cache. So we have instructions like CL flush, which flushes cache lines back to DRAM. We have CL demode, which demodes stuff from L2 cache to L3 cache. We have the prefetcher that prefetches stuff into the cache. And if you build a modern performance critical application, you have to know about that stuff, but you're not really meant to know about this actually by history, right? The Intel doesn't want you to control the cache as much. And then, of course, we have like even stranger shortcuts. So in the paper, we have two we call DDIO and IOAT. So the idea of both was actually, I think IOAT was introduced in 2006 by Intel, DDIO in 2012. The idea was if you have like networking and you have your network card and you have to move the package to the CPU, it's too slow to do it with the CPU instructions. So with IOAT, you have a DMA unit that directly moves that data into memory for you without the CPU's involvement. And we found out you can kind of misuse this to also move data between persistent memory and DRAM. I think the IoT was invented in 2006 or introduced, and PMEM was introduced like 3 years ago. So it was never meant to be used that way, but you can kind of use it that way.
A happy coincidence. Yeah.
Yeah, I think nobody even at Intel knew about that. It's like just it turned out it worked that way, which is really great for us. But there are issues. I think we'll come to them later as well. And the other thing is DDIO. This was also meant for networking, I think introduced in 2012 for 100 gigabit Ethernet. And there the idea was that you could directly move stuff from the network card into your L3 cache, because if you moved it to DRAM, it would be too slow, because then when you access it, you would have a cache miss and had to load it. So to process the package at like line speeds, you can directly DMA them into the cache. And turns out also, not meant by Intel that way, I think, is you don't only have to use network cards for that. It works over PCIe. You can just as well use NVMe SSDs as well to move data from your SSD direct into your cache. So we thought, well, great, like great stuff, right? Why not use this to like have more efficient data paths where we don't have to involve the CPU at all? Because everything here works with DMA. But the issues with like this slew of primitives is that you have a lot of different abstraction levels here. Like, is it managed by the system? Is there an interface you can use? Is there an interface, but you're not really meant to use it? Different philosophies, and originally designed for different tasks, like I said. Like we tried to use it for stuff it wasn't meant to be used. Yeah, so that's kind of a course overview about the mess we are in nowadays.
Awesome stuff. So you touched on that you can kind of use these primitives like DDIO to improve things, right? So you actually have a really nice case study in your paper that uses external sort to illustrate the potential of these primitives if we can kind of not misuse but use them in certain ways to improve how we move data around, right? So can you maybe walk us through with this example and illustrate how it can improve things?
So external sort, like we said, we want to speed up cases where your data movement is kind of predictable. And I thought like there's not a better example than external sort, right? It's very predictable in the way you have to move data, right? So you start with your data on some kind of background storage, let's say an SSD. Then you have to sort initial runs, right? Like you move small packets of data into your caches, then sort them and move them back to DRAM. So that's predictable movement, right? You know the size of the stuff you move in, you know the size you have to move out of your cache again. then when your main memory is full, you kind of have to spill those sorted runs from DRAM to some kind of background storage. That's the point of external sort if it doesn't fit into DRAM. Then, of course, later on, you have to load them back into the system. Here again, you can then move them directly into the cache because you have to merge the sorted runs in the cache again with your CPU. And then you have to write them back from, like you merge them, they descend to DRAM, and then from DRAM you have to merge them back, the merged runs back to the output storage, like at the end. So the idea here is that like those are really predictable movements, right? You know beforehand when to move what where, and also we found out there exists a lot of data movement primitives for that stuff, right? So for the first part where you load the unsorted runs into cache, you can use DDIO to move them directly from SSD to cache. Then, of course, from the cache to DRAM, you can explicitly flush them with a CLFlush instruction from your CPU because you know you won't need that piece of run again after you've sorted it. Then from DRAM to PMEM, we can use IOAT to move from one kind of memory to the other kind of memory, unbeknownst to Intel, who didn't invent it to be used that way. And then later on, we can, when we have those sorted runs on PMEM, we can move them back into cache with IOAT as well, and then move them back to SSD again. So we thought, like, you know, it's like for every kind of movement, there exists a nice primitives that doesn't involve the CPU at all. So the CPU can be busy doing sorting or other database stuff in the background, while we do the data movement for the CPU. So we thought, why not use external sort as a motivating example and for the paper and show how you could profit here.
Fantastic. And that's a nice segue into the next question is like, you actually quantified the performance gains you can get by the strategic use of these primitives. So can you tell us a little bit about how you actually went about quantifying, like kind of tell us about your experimental setup and the questions you were trying to answer? Obviously, you're trying to see how fast it went, right? But I mean, yeah, can you elaborate on that a little bit more, please?
Yeah. Actually, interestingly, fastness was not really that important to us. So we thought we had kind of two goals. So of course we benchmarked DDIO and IOAT, right? So moving data to and from SSD and to and from PMEM. The idea here was, for one, of course, are there actually performance benefits of doing it that way, right? Like if the old-fashioned way of just using the CPU to move data around is as fast or faster, why do it that way? So the idea was it should be at least the same speed while offloading computation. So you don't need the CPU to do that stuff. So like if that weren't true, like why would we care, right? But the second point, I think, and that's equally as important, is the question was, are they actually usable in the way we wanted them to use, right? Up until now, it's just like, wouldn't it be nice if we could do that? Is it actually possible to do it? Was not really, well, like you said, like nobody used it that way. I think there are some papers that did kind of that stuff, but like I said, DDIO was meant for like NICs and IoT as well. So we designed two experiments. So for DDIO, we said, okay, let's assume we want to have this case where we load unsorted data in chunks from your disk or from SSD into the cache and sort them. So we simulated them by moving data with varying chunk size from the SSD directly to the L3 cache with DDIO enabled and disabled to compare. And then we just iterated over the data in memory to like assure that it's actually touched, right? So that can't, like, you actually need to load it into the registers. And on the same time, we also run a bandwidth intensive workload at the site to really stress the DRAM bandwidth to make sure we actually could see if we have an advantage of directly loading into the cache or not. So this simulates like the system and at the same time does something completely different as well, right? We're not the only tenant on the system. Okay, so that was DDIO. And for IoT, right, the point we wanted to make is when we have the data sorted on DRAM in runs, we now have to evict them into backing storage, in this case simulated by PMEM, and then back again later on when we have to merge those sorted runs again. So in this case, we also had those runs in varying chunk size and just moved it back and forth, once with IoT enabled. And the other case where we disabled it, we just used memcopy, right? So this is the way you would move stuff from or to PMEM if you don't have some kind of DMA unit that can do that. And yeah, those were the two experiments we tried to run.
Awesome, great. So let's talk numbers then. So what were the key results of each of the experiment? What were the gains, and was it more usable as well? Obviously, there was that angle to the experiments as well. What were your findings there?
Yeah, so for DDIO, we were surprised that it actually was usable, right? We thought, moving stuff into L3 cache from an SSD, DRAM is already so much faster than SSD. It shouldn't really matter if you move it into DRAM or cache, because like the time of it takes to load something from cache from DRAM to cache is not that big compared to like you only have a throughput of like 3 gigabytes a second or something. But it turned out if you really stress the system, it makes a huge difference. Like for as long as the chunks you load fit into a free cache, like I think we had like improvements from like 1 gigabyte a second to like 1.4 gigabytes a second or something like this, and of course also reduced latency. So DDIO actually is a good thing here, right? Even if you think about really slow SSDs. The downside, however, like this was the second part of the experiment, the usability is really bad. Because DDIO, like it's not something Intel wants you to mess with. So it's either globally enabled for a device or disabled. And there are some configuration parameters, but they're not documented at all. There are like some proprietary registers in the CPU. You can kind of change some values that nobody really knows what they do, but they make it faster or slower. And I actually looked at like Intel documentation, and they like agreed like it would be nice to have some kind of parameters to change this, but this is not documented and not so well at the moment. And stay tuned. And I think this documentation hasn't been updated in the last 10 years. So. And you know it makes sense for Intel because they say like, right, we built this for this one use case, and it just works out the box and it makes it faster. So why not just use it that way? But it kind of makes it bad if you, like me, try to use it for something it wasn't intended to be used for. So much about DDIO. For IoT, of course, we also did the experiment, and we found out IoT is really great if you move stuff from PMEM to DRAM. So we have 3 times the throughput. So 9 gigabytes a second instead of 3 gigabytes a second. And on top of that, we don't have any CPU involvement at all. So the CPU is free to do other stuff. So this, of course, is great because PMEM actually is really intensive on the CPU because every move would be a load and store instruction because it's the same interface as DRAM. So great in that regard. So really awesome. If you want to move stuff from PMEM to DRAM, use IoT. On the other hand, the issue is if you move stuff from DRAM to PMEM, it's actually really bad. And we were really puzzled by that. Why would it be? Like it's fast the one way. It should also be fast the other way. Also, if you move stuff that way, like PMEM has like a really high read and write bandwidth. Like this shouldn't be a bottleneck. So to get behind this, we also measured actually the write traffic that was on the PMEM DIMM stick itself. So it comes in little sticks that look like normal DRAM DIMM sticks. And you can measure on the physical memory what is the throughput there. And it turns out it's 3 times higher there than it is on the data is actually moved. And we were really puzzled by that. Why is that case? And then we found out that IoT actually has a feature which is called direct cache access, TCA. The idea being that Intel said in 2006, right, if you move some stuff from one memory kind to another, you probably also want to do some computation on it, because otherwise why would you have moved it? So they also put it into the cache, which is great if you actually want to use it. But if you just want to move it out of DRAM into PMEM, you don't need it to be cached because you actually explicitly don't want to access it. So for one, it's slower already because we have this like detour to the cache. The other hand, also the cache is then evicted semi-randomly in the end. So it's not evicted sequentially, and PMEM internally has like a block size of 256 bytes. So it only weighs data in 256 byte blocks. And if you write randomly to it, that means you have a write amplification, right? Because you just put some data into one of those blocks and then write the whole block back if you write random data. In this case, cache line is 64 byte, but those blocks are 256 bytes in size, so 4 times the size. And you have big write amplification there. So it turns out, because of this feature, that what was a really great idea in 2006, PMEM now is slow. And the worst thing is DCA, you can't even disable it in modern CPUs. I think there is some BIOS settings in like CPUs that are 15 years old, but nowadays it's just forgotten. So nothing you can do there. So like with DDIO, it's like great in theory, but in practice, it doesn't really work out really well because hardware designers 20 years ago made assumptions that just don't hold for modern hardware anymore.
Yeah, I just wanted to ask you about when you were trying to figure out how to use these, and you're looking in the docs, how easy was that to kind of figure out, I need to change this magic number to make things go faster?
It was horrible. So there's a mix of like documentation from 2006 of some like Linux kernel maintainers that like built this stuff in 2006. Then there's like documented 2011 why they threw it out of the kernel again because it's not then you have some papers that kind of try some of the stuff. Then, there is not really an interface you can use. So we used SPDK because it supports IOAT. But then, of course, SPDK is like a beast of itself, itself that is really hard to be used. It's a mess. And of course, it's my own fault, right? Because we try to do something that hasn't been connected in that way before. So we can't expect, otherwise it wouldn't be interesting research. But I said, the idea is for you, you're not meant to use that stuff in the way we used it. The idea is Intel just built that stuff for specific workloads, and the idea is that you just buy the CPU and stuff just gets faster without you doing anything. And that is really great if you are on this happy path. I say, yeah, I have a NIC and I need 100 gigabit Ethernet, and I just can buy the newest Xeon CPU and it just works. But it's this narrow path. If you stray on this path, it's great. If you go somewhere else, it just falls apart.
Yeah, cool. But I'm convinced that we need to do something here. So we can leverage these primitives. We can do something interesting in this space. So tell me more about the data pipes vision and maybe some of the key principles that underpin this vision.
Yeah, okay. So the underlying issue to us was this kind of bottom-up design. So those primitives are designed for a specific use case. And if your use case differs, you're kind of out of luck. So, and what we want to do is we want to say data movement should be explicit. So if you have to care about it anyway, right? If you know about cache associativity and cache sizes and when to move data where anyway, you might as well do it explicitly, because the interfaces don't really work and you have to work around interfaces that don't really work. You might as well have a nice interface and have to use it, right? So we want to make it declarative. So you tell the system what to move where and when, but not how. And to this end, we introduced two things. So the first one is a type system for the location that the data could be in. So currently, if you look at the status quo, more or less everything is just kind of a pointer, right? So access to some memory location might, either the data being pointed to is already in DRAM, then it just moves the data into caches. Maybe it's already cached, then nothing happens at all. Maybe the memory area you point to was M-mapped and actually is on a slow HDD, and accessing it might just be a page fault, and you have to move all the stuff into DRAM and then into cache. Maybe it uses the OS page cache, and so on. So actually you don't really know what's happening if you just access some data. So instead what we want to introduce is what we call resource locators. And the idea is that everything is behind a resource locator. And this resource locator forces you to think about it, right? For example, you would never directly access a byte in a HDD resource locator, while you would in a cache resource locator. And this forces you to think about where your data actually is. And secondly, after we've typed our memory in that way, we can say, okay, now to move data between resource locators, which is important, right? You can't process data that is being stored on SSD. We introduce the concept of data pipes. And data pipes are pipes that kind of connect those locators. So you can think about a DRAM to PMEM pipe that uses IOT, or a PMEM to cache pipe that uses IOT the other way around with direct cache access. And the idea is that these pipes then connect between those locators, and then you have some kind of transmit call or something similar, which issues a request to move that data. And this makes it declarative and explicit. And optimally, of course, those pipes map onto existing primitives like IOAT or DDIO or whatever, or maybe even new primitives in the future if vendors introduce new primitives. Of course, there are no primitives for all combinations of source and sink, right? So you might have a software fallback for those kinds of things. But even if you use a software fallback, at least you have this notion of where your data is and where it's been moved to. And what we also present in the paper is different flavors of pipes. So the idea is that you declare, but then in the background, some runtime has to schedule the movement, when to move what where. And we have 3 proposals where we say one would be you have this blocking system, like traditional IO, where, for example, you would use a read syscall to move the data. You say pipe.transmit, and then the pipes block until it's done. We also have this approach where maybe you want to have inversion of control, where you just say, I want this data moved there, and please notify me when you're done. Or we even have an approach where we say maybe the OS could have support for pipes as well. But in summary, the vision is that we say we have those kind of implicit leaky abstractions, and we would like them to be like an explicit intentional interface where you declare what to move where.
Awesome. Yeah, I'd just like to touch on what would the syntax look like for this? Obviously, it's harder in a audio medium to kind of talk about this. But like, how would that look like?
Yeah, so in the paper we actually have like 3 different code listings. We actually show you how the syntax could look like. Of course, it's hard to describe here, but yeah, the idea is to use a pipe. What you would do is you first would declare your locators, right? You would say, okay, kind of a case of external sort. I have data on SSD, so I declare an SSD locator, which would, as an argument, for example, take like the path to the file, if it's like a file on an SSD. And then, of course, I say, okay, I want to move that data into the cache. So I would also have a cache resource locator, which says, okay, I want to move that data to be processed. It needs to be in the cache. And this is already assuming a lot, right? This already assumes that cache is kind of addressable, which is currently not really true. But nonetheless, this is the vision we have. And then, of course, you have like those 2 locators. And then you just instantiate a pipe. You say, okay, I want to have a pipe from locator A being the SSD locator to locator B being the cache locator. And this just instantiates a pipe, and then you just call some kind of transfer method that moves the data from the SSD to the cache. The idea being that, however, everything up until the transfer call is just declarative. So we tell the system where we have our data, where we want it to be, and how it should be connected, but we don't tell the system, like we don't issue calls to transfer the data before we actually need it. So the idea is that the system already knows of your intentions before you actually move the data, so it can do optimizations there as well.
Nice, cool. I guess I'd just like to maybe touch on a little bit as well. What do you think the sort of the limitations / downsides of this vision would be? Obviously, we're adding like another abstraction layer, and so maybe there might be some potential performance implications there with that another abstraction layer. So maybe you could elaborate on that for us a little bit.
Yeah. So first of all, regarding performance, yeah, you're right. It would be an abstraction that would have performance impact. So one thing is, we don't really like for us, if the performance stays the same, this is already a win. So of course, performance is important, but I'd say for us, it's more important to kind of get this vision where you be intentional about the stuff. And even if the performance of like transferring data would not be faster, the whole thing about it being intentionally and you only transfer what you actually need to transfer already probably impacts the overall performance of the system again. So yeah, but you're right. This is one possible downside. There are the downsides. So another downside is it's not really applicable if you don't know where to move data beforehand. So in like this big data intensive workloads, that's easy to know. But like if you say like have a system that has a lot of transactional database systems, you might have a lot of erratic random reads or writes where you really don't know beforehand because you don't know when the user will start a new transaction. In that case, pipes are not really a great fit, I'd say. So if like, moving data around is not your problem, pipes might not be the fit for your problem. And of course, pipes kind of want to use the primitives, optimize primitives, right? So if we already have primitives, pipes work great. If we don't have primitives for some kind of device pair, we would like to have the primitive for that pair, but it's asking a lot to go to Intel and tell them that right now, like we have this vision, like please build this thing. So we don't think that's like a way we can go. So yeah, it's kind of dependent on there being primitives to use. So we think with the primitives that are already there, it's already a good thing. And like I said, you can have software fallbacks, and even if you just use software, we think that's a good abstraction to have. But optimally, we would have more primitives there as well.
Awesome stuff. You never know, right? It could become so popular, hopefully, that it actually then the kind of feedback loop, Intel actually motivated to kind of almost like kind of fall in line a little bit or kind of help out in that sense. So maybe we'll see, I guess.
But I think the issue here is that Intel really it's just a mismatch of what the goal is, because for us it's like we are experts in the system and we want to use it to the fullest of its potential, and we are in the database community, we think about that stuff, right? Like how can you optimize for caching and so on. But for Intel, like they want to sell the customer, you have like this big legacy application and like just use our chip and like we built this custom like kind of accelerator for exactly your use case, and it will get faster, and you don't have to do anything. And for like, this is a big selling point for those people because they don't build new systems; they maintain like big legacy systems. So I think this is kind of the crux here, that there are different kind of goals to optimize for.
Cool. Okay, so where do we go now next with data pipes, and what's next on the research agenda? How do you go about realizing this vision?
One thing Intel already announced, I think it's already released with Sapphire Rapids platform, the data stream accelerator that already like tries to unify all this stuff a little bit. So we would like to, of course, look at that. We really didn't have hardware or the time with the data pipes paper to do that. And of course, there are lots of like open questions to tackle. Like it's not secret. This is mostly a vision paper here, right? So we have some code to prove that stuff, but like it's not an implementation you can just use in your code. So I think a big open question is, for example, how could we schedule the data movement, right? Like currently we say there's probably some kind of runtime. You tell it to transmit data from through this pipe from A to B, but how does this runtime actually look, right? Is it just like, does it just run on an additional core? It's like just some kind of library in the background? Maybe would it be an OS feature that your operating system would support data pipes as like native thing, where you can then just fopen dev/SSD pipe or something like this? Or even thinking further, we thought a lot about like cloud context, right? Like, for example, in the cloud, you have big issues with like noisy neighbors, right? If you have like two people running on the same hardware and one like tries to do a data intensive workload, it might steal resource from the other one. And for that reason, they have to over provision a lot, right? So that if something like this happens, they can kind of buffer it. But if you had data pipes, of course, in the cloud context, your system would know about your intention to move data and could schedule it more efficiently. So in the cloud context, we think it could reduce a lot of issues of noisy neighbors, and therefore you don't need to over provision as much, which makes it really enticing for cloud vendors, in our opinion. So yeah, cloud context would be another thing we would like to look into.
Cool. Awesome. Yeah. So I mean, for my next question, obviously with this being a vision paper, there's not necessarily a tool that a software developer can go away and use today. But how do you think kind of data engineers, database administrators can leverage the findings in your research, and kind of maybe longer term, what impact do you think it could potentially have?
I think, yeah, like we said, it's a vision paper, so you can't just take the implementation and make stuff faster right now. But I think the biggest takeaway should be that the paper should inspire people to be more intentional about the data movement and think about what's actually happening below the stack. Because we're like building abstractions on top of abstractions on top of abstractions, right? Like if you nowadays, like I said before, and if you access a pointer, you have no idea what's actually happening. Like, of course, you can find out, but in general, and then people are happy about that because it's easy. But I think if we throw away a lot of those abstractions and re-engineer them in a way to be like more close to the hardware, like for example, data pipes could be a pretty thin wrapper around like those primitives we talked about earlier. You could get an interface that's not a lot harder to use what we have, but could give you a lot more benefits and performance benefits. So I think the takeaway here is think about how data is being moved in your system. If you think about, for example, like Postgres or something, like database systems, they were engineered like 30 years ago, and their whole thing is that they say, right, HDDs are slow. We don't need to care to optimize a lot other stuff in the beginning because we are IO bound anyway. And like I don't fault them for it, right? Like this is how it has been. But if you throw away this assumption nowadays with the hardware you have and the accelerators you have, you might have engineered the system completely different. Just thinking about that, I think, could bring some benefits.
Yeah, for sure. I was just going to say that the general awareness of this is I think in itself has potential for big impact. So yeah, cool. Whilst you were working on this, obviously you've kind of touched on you've kind of gone deep into the weeds and setting like loads of different sort of primitives and different sort of pieces of hardware and whatnot. So if you can kind of capture, what was the most sort of interesting thing you kind of learned while working on this paper? Maybe the thing that kind of caught you off guard as well.
I think the biggest thing probably was like the difference between theory and the real world. So it's not my first paper, right? So in my previous papers, in the beginning, I said like I would like to do this, and then I mostly achieved that. Of course, there were like setbacks and roadblocks and like detours and bumps on the way. Otherwise, it wouldn't be an interesting research paper. But in the end, I more or less did what I intended to do. And here, the story of the paper more or less completely changed half the way through, as we didn't really found a way to achieve our original goal, because our original goal was actually to build this merge sort thing, and say like, see, like you can build a really fast merge sort, and then I started implementing it, and I found like we talked about earlier, found lacking documentation, interfaces didn't really work. You had to use opinion frameworks like SPTK and so on. Like it got really messy. It turned out, let's not write a paper about this merge sort, write a paper about like how messy it is and how could you do it maybe better. And turned out that like embracing those difficulties and making them to a story in the end really worked out great. And I think the paper really got better because of it, because I'm pretty proud now that our paper solves a problem that I know it exists because I encountered it while trying to write a different paper. So yeah, I think the biggest lesson here is to like embrace failure, I guess. Like I was like not happy when it didn't work, and I go, no, like sleepless nights, right? Like the whole paper falls apart, but then it turns out actually it made the paper better in the end, I guess.
Yeah, that's good. I mean, I normally ask kind of about the origin story and the background of the paper and how bumpy that journey was from the kind of initial conception of the idea to the actual end paper. But it seems like the whole thing changed on you halfway through, which was, I guess, unpleasant. But in the end, it worked out for the best, right?
Yeah, and like I said, the thing that kind of held the paper together, however, from the beginning to end, was that we had this idea, right? We have those well-behaved algorithms, and they are about data movement, and how can we make this work? And I think this was like the core of the story from beginning to end. So I think this helped us, that we said like, yeah, but we have this problem, and maybe we approach another aspect of that problem, but we still try to solve this problem about how can we have those well-behaved workloads where we know what data moves from when to where? How can we make them better?
Sure. Just out of interest, I mean, obviously, a lot we're kind of building off this assumption, having that well-behaved algorithm, just so we can kind of control, I guess, the state space of things that can kind of go on. But how do you think it would perform on certain algorithms that are maybe a bit more unpredictable?
Yeah. So this is an idea we had like halfway through the paper. I think that in actuality, if you think about data structures, all they do always is try to kind of make workloads into well-behaved workloads. So if you think about like B trees or hash tables or whatever, or like let's say LSM trees, right, where you try to, LSM trees are like this append-only data structure where you like try to append new data and in the background try to merge them to make like sequential reads and writes all the time, because they're optimized for disks where sequential reads and writes are king. And in the end, right, like for example, if you use like some key value store with an LSM tree backing it, this workload is not well behaved. You have like random reads and writes coming in all the time, but the LSM tree kind of forces your erratic workload into a well behaved one by making it well behaved by being append only and then being a sequential write. So I think you can make most not well behaved workloads into well behaved workloads by thinking about the right data structure. And yeah, we thought about data structures about this like workload transformers, which try to transform them into something that then again could benefit. Like I see an LSM tree could benefit from a data pipe because it's really predictable then. But of course, there you have to build stuff on top that's like not covered by the paper, right? You need the right data structures to make that work.
Yeah. Yeah. I guess also as well, what sort of other research are you working on at the moment? I mean, you've mentioned before that this isn't your first paper, right? Fifth year PhD student. You've been through this process many a times. So kind of what other research are you working on at the moment or have been in the past?
Yeah, so my first big thing was actually analytical query processing. So and there actually, right, price matters a lot. Like you have this big cloud databases where we have to read a lot of data, and like hardware becomes a commodity and you need to be cheap. And there I built like Mosaic, which was a storage engine which can fetch the data for you, right? It's like part of the database system, but it also can recommend you what hardware you should buy to maximize your performance for the given budget, right? So the idea was that it says, right, like 80% of your data you don't read anyway, so you might as well put it on the cheapest storage possible. And then it draws you like this nice Pareto curve. Is like if you increased your budget by 10%, you could increase your performance by 30%. On the other hand, like if you are out of budget, like if from 80% of the budget, you could still have like 95% of the performance or something like this. And I published this as VLDB 3 years ago. And then I said, okay, enough of analytical, let's do transactional. And then I built Plush, which is a persistent hash table for persistent storage. And it kind of tries to be an LSM tree at the same time as well. So the idea here is that persistent memory has a really low write latency, like insanely low. So it's comparable to DRAM, and at the same time being persistent. So we thought, why not leverage this to have like a data structure that can cope a lot with inserts? And so we take the best of LSM trees and apply it to hash tables and let this work on persistent memory. Unfortunately, Intel now killed persistent memory, which I'm still very angry about because I think it's such great hardware. Like it has such low write latency. It won't be reached in the next decade by anything else, I guess. But I guess it just didn't make it profitable enough for them. So turns out they killed it. Yeah, so those were the big other two papers I wrote in the past. The second one being on VLDB 22. But now, we think about some follow-up for data pipes, but I probably won't be the primary author for that because I'm currently in the process of finishing my dissertation. So.
Cool. Yeah. The next question, I like to ask this to all my guests, and it's really interesting to see how the responses diverge. It's about the kind of the creative process of generating ideas and then selecting which ones to work on. So I'd like to kind of get your take on how you approach this.
Yeah. So I think I never really had a structured approach there. So what I did is I said, like, let's do whatever sounds fun and interesting at the moment within reasons. So I had this discussion, I think, after my first big paper with like my supervisor and some senior lab members. I said, like, right, like I did this mosaic thing now, right? It's on VLDB and it's great and I like it. Should I now like look into different aspects of that and like how can we do it in the cloud? How can we do it fast? And I said, of course you can do that, but that sounds pretty incremental. And also, you will never have the chance in your life to be as self-guided again as you are now as a PhD student. So just do what is fun, right? So because you have the opportunity now. So I thought, yeah, okay, like PMM sounds pretty interesting. New stuff from Intel, upcoming technology. I didn't know that it would be killed a year later, but still. And I did analytical. Now let's try transactional stuff. And so I came to that. And I'm very grateful for my supervisor, of course, because he allows me that freedom, right? He says, like, yeah, as long as you do some interesting stuff, it's fine. So I really, yeah, my way to do it was just like do what seems fun within like the confines of like the general topic that has to be done, because
Awesome.
I try to enjoy my PhD and do what sounds interesting to me.
Yeah, as a guiding sort of principle, if it's fun and interesting, right, then it naturally is it makes enjoy working on something more enjoyable, and therefore maybe you generate more ideas based on the fact that you're enjoying it, right?
Also, my supervisor once taught me the issue is, right, you can do a lot of follow-up stuff on stuff you already did, but as soon as you exactly know what the path will be, it's by definition not an interesting research topic. But because, if there isn't the possibility to fail, it's probably not something very new or novel. So, right, do something out there, right? Maybe it fails, but as we've seen in the data pipes paper, it still turns out interesting. And like if you just let's write 10,000 lines of code and then this will just work, it might also be a nice paper, but I think it's definitely not as interesting as something that's totally out there and might as well just not be worth it.
Yeah, I think you hit a nice point there, and also as well the fact that something doesn't work in itself can often be interesting, right? Like it doesn't have to be when you start out the end goal doesn't have to be this perfect, amazing, super fantastic system or whatever, right? Like the fact that you tried something and it failed is in itself an interesting result a lot of the time, right? And yeah, And maybe it's harder to publish that sort of stuff, right?
Yeah, unfortunately, it's really hard to publish negative findings, I think, still, because like there's still the stigma of why should I care? I think it would be a lot better as a research community if we encourage that more.
Yeah, I agree with you there, Lucas. Yeah, for sure. Cool. I guess kind of on that a little bit. Like, what do you think is the biggest challenge in database research at the moment?
I think I have two answers. So the first one would be, let's say, outward facing. So I think the issue is to get people outside of our community to see how great database systems are. So I talked a lot with like the bioinformatics people at our university and also like machine learning people. And, they do a lot of stuff outside the database system, right? They just use the database system as like the store of data, and then they do all their stuff in Python. And then they like try to reinvent joins and sorts and like do all of this on the application level. And of course, we can now like point at them and say, obviously you don't know how it's supposed to be, but I think it's a failure on us that we as a community didn't get those on board to build the tools into our databases for them to use. So I think we should invest a lot more into like the tooling to make it easier for such people to use our systems and show the advantages. For example, if you look at DuckDB, they just like build a really easy to use database system. It's like 2 lines of code and it works, and it just can replace whatever else people used beforehand just out of the box, and it has great adoption because of that. And I think we totally missed the goal there in the past. So I think that's a direction we could go in more. And then I think inward facing. So I think that's like the TU Munich thing, where we say people leave a lot of performance on the table. So like we talked about earlier, we build abstractions on top of abstractions. We build like Spark clusters with lots of instances and lots of nodes. And I think if we really carefully engineer the system, we can do a lot on a single node. And but it's like really hard work to do. But I think especially nowadays where like performance doesn't scale as nicely, like slows down the improvements over the years, it is worth a lot if we maybe refocus a little bit and try to get out the most of the hardware we actually have standing around and is mostly idling.
Yeah, I totally agree. Two really interesting like challenges facing us there. When you were talking about the outward face one, like the first thing that came to mind was DuckDB. They've positioned themselves perfectly of solving that sort of like usability problem and getting it in like getting data scientists and data to use databases, right? Because I've similar sort of experience to you there, like people in bioinformatics and other sort of areas that they don't want to touch a database, right? Because a lot of the time it's kind of hard to install and hard to operate. They're just like, no, I'll just reinvent the wheel myself in my own hacky way, right? But no, yeah, totally agree there. And also again on the inward facing kind of direction as well, I feel like the people a lot historically have been like, yeah, we want to make this distributed, we want to get as many nodes, throw as much compute as possible, and that doesn't necessarily give you the best outcome, I don't think. So like you say, we leave a lot of performance on the table. I'll have done in the past. So yeah, interesting stuff. I guess it's time for the last question now. So what's the one thing you want the listener to take away from your work and from this podcast today?
Yeah, so I would say the main thing is we shouldn't try to hide the complexity of what is happening below us on the stack. So we should be aware of it. And of course, not everybody can manage all the complexity, and not everybody should. So I think we should have nice interfaces helping us to deal with that complexity, and we should think about them. And I think we all agree, if CPUs were invented last year, exactly with the performance they have now, we would probably have chosen a lot of different abstractions for the stuff, because a lot of stuff is just grown over the years because it was a good idea at the time. So I think we should take care of that and think about how we could re-engineer stuff to more better fit the current landscape. And so I would say, like, if you're concerned at all with performance, think of what happening is below the stack, below you in the stack, and how could we better speak with that part would be the big takeaway for me.
Great stuff. Well, let's end it there. Thanks so much, Lucas, for coming on the show. It's been a fascinating conversation, and best of luck with the write-up. I hope that goes smoothly and you hit the Q2 deadline. Great stuff. If the listeners interested in knowing more about Lucas's work, we'll put links to all the relevant materials in the show notes. And if you enjoy the podcast, please consider supporting the show through Buy Me a Coffee. And we will see you all next time for some more awesome computer science research.